Hear me, guys?
Arnold,
Yeah,
how are you, mate?
All right, I'm great. Tell me, Sriram,
Good,
how are
good. Hey,
you?
sorry. Yeah, good. Sorry about the 20 minutes past time. How did your meeting with your friend go?
Oh, excellent. I didn't for the first time, but I've known him for a while uh, virtually.
Okay,
He's a fellow maker from Bangalore.
okay.
The more
Nicely
exciting thing
done.
was he was bringing in a nice parcel from me from another friend of mine who has gifted me a vintage Commodore 64. So,
Indeed, indeed. Okay, okay. How did you come across Commodore 64? It's a classic.
yes, it is. It belongs to this extremely close friend of mine. In fact, I've used that computer when I was in Bangalore in the
Okay,
80s.
okay,
So he
okay.
felt I was the only one fit to receive it from him. So,
Good to hear, Arnold. I know it's almost 10 o'clock there, so can we tap into your calibration expertise for the next half an hour or so? Do you have the time,
yeah,
please?
sure, we can.
Wonderful. Agni, would you like to run this in terms of the questions you have? I know that you're developing a calibration procedure for us. So maybe you'd like to run this hangout, ask Anu some questions. If you can figure out a structure for what we're doing, that would also be great, at least the seed for what our next steps are. Agni, over to you.
yeah, yeah. Hi, Anul. I
Hi.
would want to know, like the thing what we're doing is we're trying to develop air quality sensors.
Yep.
So, first of all, I would want to know, like, how exactly, just to begin with, how exactly do you define calibration? Like,
Okay.
just to start.
Yeah, okay. If you have another question, let me hear that, or I can answer this part first. Okay.
Agni,
Uh,
Anu's go ahead.
So
Yep.
the most likely the way it could work is, it, of course, that this is related to gases. Like
uh-huh.
when you calibrate sensors that detect specific gases, what you get is what are known as calibration gases available in
Mm.
canisters.
Right,
Uh,
right.
these are specified to a certain level of purity in terms of the amount of, uh, let's say, basically in percentage. So how pure is that particular gas? It could be
Mm.
nitrogen or oxygen or any of the other gases that you're trying to calibrate.
Great. Interesting.
Uh, but just having that canister of gas doesn't really help. So you also need to have a method of introducing it uh, in a chamber and then having two sensors to do the measurement. One is your standard sensor and then the unknown sensor. Then you compare
Right.
readings between the two and sort of create a kind of a chart that gives you an idea of how linear the unknown sensor is.
Mm. Mm.
So it involves quite a bit. It involves access to certain materials, as in these calibration gases, and
Right.
access to certain physical artifacts like the test chamber and so on to carry out the test itself. Also, the test needs to be done at controlled temperature and pressure as well. Pressure is not a big concern as long as
Mm.
uh, it's within a reasonable level above mean C. But temperature, yes, makes a big difference in measurement. So
Mm.
you also need
What
controlled
about you?
environment. A controlled environment includes both temperature and humidity.
Okay.
Anu, could you explain to us why physics-wise temperature is an issue?
Uh, well, it's basically the entropy of the gas, right? So
Exactly. Okay.
uh,
But how does
more or
that
less,
affect concentration? How does pressure affect concentration? Clearly,
uh,
the more pressure in a unit volume, the more molecules in a unit volume, and
uh,
therefore the more. Is that
actually,
the basics?
not a lot really if we are doing comparative measurements. So like in calibration, you can do two types, right? Absolute or relative. So if you're doing relative measurements where you have one
That's
sensor
true.
being compared to a second one, and if both are in the same environment, then
Good
you're going
point.
to get more or less, you can ignore variations in some of the external factors to a certain extent.
Good
When
point.
you
Good
go
point.
down to, again, calibration is done in certain levels. Like, okay, Echelon 1, for example, is what national standards are. So,
Hmm.
the national standards in India or NIST in the USA and so on. Those are the highest
Right.
standards. It's very difficult to, I mean, they are the ones who maintain it. And then there are secondary standards or echelon 2 standards which then come down. And then from those standards, you come down to tertiary standards and so on. So there's quite a few levels in this whole thing. And it all boils down to accuracies and tolerances as you go up or down the whole pyramid.
Hmm.
So at that point, you need to figure out what is your acceptable level of accuracies that you're looking at, and
Definitely.
once you are defining that, you then have to look at a level higher than that as a comparative or as a comparison standard. So it
Hmm.
should be that's essentially how you would try and go about it.
Right, right. And we have to perform a thorough calibration procedure because a lot of these devices are not calibrated for large dynamic ranges, typically for one or two temperature, relative humidity settings. So
Right.
it's incumbent on us to develop a full profile. Isn't that right?
Exactly. Yes. Uh, yes, you would have to basically linearizing the sensors is quite a task by itself. The other
Right.
problem with environmental testing is the amount of time needed because you need a fair amount of time to make even minor changes in your setup. So let's say if you have a concentration of 5% and you want to go up to 10%,
Hmm.
uh, it's not going to happen instantaneously. Your control systems and other things are going to take quite a while. It's much easier with electrical phenomena. You can just change voltage from 5 to 10 volts. It
Hmm.
takes
Hmm.
a couple of milliseconds for it to stabilize. Uh, but mechanical and physical properties are extremely difficult to stabilize and maintain at these levels. So,
Right.
which is one of the reasons why they don't take a lot of readings when doing this kind of calibration. But it just takes up too much time, which
Right.
boils down to expense. So,
Good point. Good point.
and which is why you want a linear sensor so that even if you have just 2 points of calibration, and if the sensor is linear, then you know that you
Excellent
can
point.
extrapolate. If it is
Excellent point. Hmm.
non-linear, you're going to have a lot of trouble because there's just 2 points won't tell you anything at all.
Good point.
You can
Definitely.
fit many curves to it. So you'll have to have. So one is to look for sensors that are linear. That makes your job easier. Because
Hmm.
sometimes you could actually even make it with 1 point calibration.
Hmm.
The
Hmm.
slope is not.
Exactly. Agni.
Anul,
Agni. Yeah.
Yes.
yeah, yeah. So the thing is, we were talking to people from different communities. There's this
Yeah.
community called Airbeam. So
Yes.
what they do is they calibrate it with respect to a fourth order curve. Can you explain? Do you have any idea why?
Yeah. So that's curve fitting. That's where the non-linearity comes in, right? Because
Hmm.
uh, it's it's not like a plain resistance or a voltage which follows a linear curve. So fourth
Mm-hmm.
order would be x raised to 4. That's quite a complex curve fitting. Uh,
Yeah.
what that also
Um,
means is you need a fair amount of data to achieve that amount of curve fitting.
hmm. Hmm. If I'm not mistaken, Agni, just to add to what Anil was saying, the only
Yeah.
way, the closest approximation between reference and
And
actual sensor is a fourth order curve, where it would be a linear y equal to mx plus c ideally.
Mhm.
This is unfortunately the only way to fit it to get the best possible R squared is through a fourth order curve.
Okay. Okay.
Is that right, Anil?
Yes, it does make sense, certainly.
Okay. And as
And
Anil was
it
saying, the
has.
problem, yeah, go ahead, please.
Go ahead, Ram. Go ahead.
Now, I was just saying that unfortunately that increases the complexity of the calculation. It takes time,
Yes,
but
yes.
hopefully
Indeed.
with floating point, if we can find a decent processor, that shouldn't be too would that be done on the server side, Anil, or would it be done on the sensor? Could you explain that aspect?
I didn't get you. Can you come again?
Would a lot of these, once we have the calibration curve established, hopefully most of it will be linear, some part will be non-linear, perhaps especially in the higher concentration ranges, non-linearity starts to increase.
Yeah.
Would once the calibration curve is established for low to a high dynamic range, will the processing be done on the device, or is it typically done on the cloud?
It's difficult to say. You could approach it both ways. Uh,
It would depend on the architecture, right? If the hardware is capable of running
a lot, yeah, a lot.
Mm.
At this point, I think so right now our challenges are more in the calibration side, right? Rather than the other thing I can foresee is if we can get the manufacturer to provide uh, the variance data, that means between the batch of sensors that we are making, what kind of variances we are getting, then we can start becoming more generalized about the calibration itself.
Excellent point. Agni, did you gather that?
Yeah.
So he's talking about
Yeah.
basically intra-calibration, the intra-sensor variation as well.
Exactly. Yeah.
And then we can probably do a mean on the standard deviation, the variation, then use that for any further calibration.
Exactly.
I see. Also, Anul, gas sensors calibrate differently to particulate matter sensors. The difficulty here is certain sensors need to be calibrated again, and certain sensors like particulate matter sensors don't need to be recalibrated on field.
Okay. I don't have much experience with the environmental sensors per se, but from what
Okay.
you say, yes, it seems obvious. Uh, Mainly because particle sensors work on a different principle, right? They're mostly laser interference based kind of things. So that's pretty much an absolute calibration. All it needs to do is count uh, particles, and the volume is known. So as the air passes through the sensor, over a period of time, how much particles it counts, something of that kind.
Correct.
So it's actually just a counter. There's really not much
Exactly.
to do in terms of calibration. Gas sensors, on the other hand, most of them, I believe, are working on the heater principle, I assume. So you all have a little heater that there is some active element on it, to which the gases adhere to, and that changes the resistance, I guess.
Correct. Could you explain this important point about why we need to recalibrate? If you've established a calibration curve through initial experiments, why would one need to recalibrate after the initial factory calibration?
Okay, that's due to factors like drift and aging. You need to recalibrate practically everything. You can't calibrate one, whether it's electrical, mechanical, whatever. When you do it once, you can't say that it's going to last forever.
Is that because of inherent?
Yes, there is inherent drift in the sensor itself. As over a period of time, as you keep the heater on, it loses some of those active elements that it has.
True.
Changing its performance. Then there's stuff like aging as the unit is used more and more. Also changes because of actual field use. So you're calibrating it at, let's say, 25 degrees, but out in the field it's been subjected to 40 degrees for a fairly extended periods of time. So that changes the whole physics of the sensor itself.
Shouldn't it be theoretically possible to add an additional factor of time and then use to suggest that the calibration curve changes with time? Shouldn't we be able to account for that also in the calibration curve?
No, the effect of time. Recommended is, for example, this is just as an example to give you how it works. Let's say you're using a vernier caliper and it's calibrated today. When it needs to be recalibrated, depends a lot on how you're going to use that thing, right?
Mm.
And that is left to the user to determine. The calibration standards laboratory cannot tell you that you have to come again after a month or 2 months or 6 months and get calibrated.
Right,
What
exactly.
they will tell you is if you're going to use this every minute of every day for 8 hours a day, you probably have to come back again within a month to recalibrate because it's going to wear out much faster. However, if you're going to use it just once a week, you can probably be sure that it's going to stay within calibration for a whole year before you
Mm.
need to check it again. So
I
this is
see.
going to be use based. We will have to figure out
Mm.
based on uh, data that we gather, how often do we need to recalibrate the sensors.
Good
So
point.
this
Good
means
point.
we'll have to have control units out in the field which we can calibrate as often as we can so that we gather data and see how things are moving or drifting in them and apply that as kind of a corrective mechanism to the rest of the sensors.
Interesting. 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 Um, Agni, I have several questions for Anul. Would you like to? I know you're
At this
running
point,
this.
before
Yeah.
I forget, I'd just like to add
Yes.
Yeah.
that whenever you decide to deploy, it would be nice to have a couple of these control units installed in controlled environments.
Yes.
Uh,
I see.
so
Excellent point.
let's say an air quality air installed in an environment which doesn't have dust and particulate matter and so on. So that acts as a reference and we calibrate it quite often and gather data from it and see how that is drifting vis-a-vis those which are being exposed to the elements, temperature, humidity, rain, dust, smoke, and so on, and how those units are performing. And then take that
Interesting.
data.
Interesting. So this allows us again, in principle, to determine what the mean effects of time might be
Yeah,
on
yeah,
these values,
exactly.
and then introduce that as an additional factor in our calibration
Yeah,
curve.
yeah, yeah.
Understood. Excellent. Excellent. Thank you for that, Anil. That's a great idea. Agni, over to you, Matt.
Yeah,
Yeah,
yeah. So in the event of using, chemical sensors,
yeah.
we found that people were using like just using the data sheets to calibrate the sensors, which
Okay.
turned out to be a pretty bad method to do it. Now, the issue with these calibration methods is that you really don't know how this would react in general, right? What I'm saying is, will it always, let's say, if it reaches a saturation level,
Okay.
it's the maximum that can reach. It does take some time to fall back to its correct value, right? So,
Yes,
how
it
do
will.
I separate this noise from the data?
Like I said, just having enough data, that's one. The second is the response to
The settling
oversaturation
time.
is, yeah, so that's oversaturation. It's got too much of input and more or less it gets oversaturated. Uh, that's something that is really beyond your control. So you just have to live with it in terms of maybe
Okay. Yeah.
one method would be to have a secondary mechanism which,
Hmm.
let's say, monitoring CO, carbon monoxide, and you don't want it to reach beyond 80%. And I'm just giving some numbers.
Yeah.
Hmm.
So when it reaches 75 or 80%, we just close a window over the sensor to protect it from further exposure to concentrations above 80%. That prevents it from getting oversaturated. Once the trouble being that at that point you also don't have any further idea of what the concentration is because you closed
Mm.
down the sensor.
Right.
So you have to decide between whether you want to protect the sensor from oversaturation or uh, live with the delays associated with its measurement going oversaturation and then waiting for it to again come back to normal. It's not an easy task really.
No, that's a big decision to
Yeah,
make, Agni. We have to decide if we want to throw out the data or to categorize it and do a
yeah,
histogram on the number of the time on which it's been above a certain value.
Yeah.
I was saying to Agni and all that
yeah.
that one of the things we can do initially is at least to look at the relative changes in values, or to look at
Yes.
whether it's hazardous, or to follow the air quality index. And if it's
The
above,
problem is, Sriram, yeah.
yeah,
Continue.
Go ahead. Not a worry.
So what happened was we were testing the air beam. So what we did was we took some agarbatti and we focused it in a bottle. So only the mouth of the bottle was able to exude the fumes, right? So what I did was I connected the air beam, like coupled it quite literally to the mouth of the bottle. Now what interestingly happened was instead of saturating, the values fell down to 0. So
Maybe that's a
so
function that they programmed in. Okay, I'm not sure how the code works, but that could be a result of their code kicking in to either disable the sensor or I'm not sure.
I'm glad you found that, though, Agni. That's a good point to take up with the developers to find out why that might happen. That's going to be obviously important to verifying our data down the line. So please note that down. We'll take it up with Michael, the developer, separately.
yeah, I believe Venkat has the data recorded as well.
Okay, that's an interesting find. That's a good way to do it. That's a smart way to use agarbatti. And I know people have used talcum powder and things like that. So they've taken glass wool and basically scraped it against a solid piece of talcum powder, and then the chalk dust that's been raised by virtue of the scraping, that they've measured. So, like Anul was saying earlier, you ideally have challenge concentrations in exactly the right parts per billion or parts per million. Or you do this kind of, jugad, this really clever way of using talcum powder and doing it as well. Right, Anu? Because these gas chambers and PM chambers tend to be very expensive as well, don't they?
They would be. I mean, plus you have to, the reference sensor is going to be quite an expensive part of your whole thing.
Indeed.
And that in turn would have to be calibrated at a laboratory which has an even better standard.
Exactly.
So that chain has to be established until you reach a certain level.
Precisely.
Definitely.
Quite a challenge. Do we have any idea how the air quality guys or the other folks are doing the calibration stuff? They shared that with us?
So, from what I've understood from initial chats with Dirk Swart, one of the lead developers on the air quality, he tells me that they basically have the factory do a 1-point calibration on relative humidity and temperature. And then they do a zeroing. So they don't do they don't determine a calibration curve. They zero the sensors to make sure that at least bias is taken care of. And then they essentially ship the sensors to consumers. So one of the important tasks that we need to do is to come up with a calibration curve for the air quality.
We have been designing one.
So one single point calibration. Let's take the case of humidity. What is the value that they were using for that 1 point? Is it like 80% humidity or 70%?
I think they were saying 25 degrees Celsius, and I will have to come back to you on the RH value.
Okay.
But it was a 1-point calibration, obviously 2-point, it's X and Y, but that's all they were doing, and then zeroing in a simple chamber that's set up and then shipped off to consumers.
What I would have probably done was ask the factory to do a calibration at, let's say, 80%. And then at my end, because I know I can achieve 40% humidity much easier and more control, at my end, zero it at 40% humidity. Then I have a 2-point calibration that I can fall back on.
Interesting. So we can ask them to do that. I will get in touch with the air quality guys and find out what their calibration procedures are. So Agni, a point to note, we have to find out from the developers what their calibration procedures are.
Definitely.
To get it in detail from them written down as well would be useful, I think.
Okay.
And going back to your earlier point, Agni, that we were discussing about what to do with these high data values, like Anil was saying, we just have to bite the bullet. When it goes into saturation, there's no way of extrapolating from there. That's where averaging and not taking second values but looking at 30-second intervals or a minute intervals would help us with that. We do lose some accuracy, but we also reduce the noise by virtue of that, I think.
I guess so, yeah.
So we increase the signal to noise ratio, but that's something I think will be proved out by testing.
Right.
Anul, go ahead, Agni. Go ahead.
I'm sorry, I'm continually interrupting you.
Not at all, not
Uh,
at all.
so the thing is, one thing that I have been constantly pondering about is how high is high enough? Like, you have a reading, right? I'm calculating in micrograms per meter cube.
Okay.
Now, how high is the maximum value do I read? Because we did a barbecue test. What we did was during a barbecue, we put the air beam out there, and we quite literally received a value of 16,000 micrograms per meter cube.
First up, what were you cooking, Agni? Sounds very tasty. Anil, any thoughts? But you get 16,000. I've never seen value that
So
high. Okay,
that was from the smoke detector.
right.
That was from a PM 2.5 detector, air beam.
Okay. All right. How high is what the standards are there for. They are supposed to tell us what is a good range and what is not. Uh, that's what we're trying to measure basically, right? That's air quality. So we have
Yeah.
to
So
look up
just
on the
abiding the standards
standards.
are enough.
Yeah, we have to. But that's what the standards
Yeah,
are
okay.
there for, to guide us on what is a good range and what is not.
Definitely.
What was your specific question, Agni? Are you saying what do we do with such high values, or is it possible to get such high values at all?
No, what I was asking is, we do have a standard range of values that we're expecting.
Hmm.
But what I was asking is, let's just say that the sensor is supposed to be calibrated till X limit. Do I go
Correct.
over it to calibrate, or do I just leave it at that? That's my question.
No, as far as calibration goes, you never go beyond range. Calibration
Okay.
always sticks to the range. Field use, it is possible for the sensor to be rated for, let's say, 2x overload, for example. A lot of pressure
Okay.
sensors, torque sensors have that kind of uh, specifications that you can over torque a sensor up to 5 times its rated torque. But that wouldn't figure out your calibration patterns. You just
Hmm.
calibrate with rated range and leave it at that.
So what will happen when we get a raw sensor value that's more than what would
Uh,
fit within the calibration curve is we either throw it out or we assume that's the highest possible value and then calibrate for that value. Would that be
yeah,
it?
exactly. Or you could just put it as an overrange signal. That's it. Leave it at
Right, right. I think that's what we might have to do, Agni, for the sake of QA/QC, to say that
that.
these
Yeah,
are too high
exactly.
and to note it down. I mean, we
Yeah,
specifically noted down that we've thrown these values, so that's part of QA/QC as well. That's okay too.
yeah. So you don't
Agni,
have to
does
put
that?
a number, but you just say that it's
Right,
beyond range, which
exactly.
obviously means it's not all right in any case.
Exactly. Then we make a note saying, hopefully, with time, there'll be calibration curves that account for these higher values too over time.
Maybe
Right.
as we gather more data, we can become more confident about recording those as well. But
Right. Right.
in the absence of manufacturers not giving us that data, we have to generate our own figures to quantify these phenomena.
Anil, you mentioned something very interesting of an intermediate calibration standard. Could you explain this concept of the primary CS and the intermediate calibration standard of CS?
Yeah, because let's look at it this way. It's a whole long chain, right? We're buying a sensor, and that's made by the manufacturer. The manufacturer tests it against a sensor that he has got, which has a higher and better accuracy compared to what he's manufacturing. That particular sensor, in turn, is then further calibrated against something that's of an even higher uh, accuracy at a national lab like NIST or EPA or whatever. So basically, it's a whole chain that ends at the national labs of each particular country. In the
Hmm.
US, it could be NIST. I don't know if NIST is involved in environmental calibration. It probably could be the EPA. Back in India, it ends up at the Bureau of National Standards, BIS.
Right.
So, having said that, basically, what you need is just one reference standard which is more accurate than the one that you're trying to calibrate.
Hmm.
Uh, So in terms of let's say limits of error, if your gas sensor has a resolution of 1 part per million, that's the least that you can measure, then your
Right.
reference or your standard needs to be at least 10 times better. So zero point 0.1 or
Oh, okay.
something like
Is
that.
that the general guideline value?
Usually, yes. Sometimes you can't find that X10 times of resolution in all cases. Sometimes reference standard is just 2 times better than what you have. Uh,
Okay.
in very rare cases, actually, it could even be just 1 time better,
I see.
almost 1:1. But that's really very rare because 1:1 is hardly an order of magnitude better. But
Good point.
certain parameters are such. In this case, gas and particles and all are not very easy to uh, sense and calibrate and generate accurately. How do
Hmm.
you generate an environment which is exactly 10 ppm? It's
Hmm.
going to be extremely difficult. Right?
Hmm. Hmm.
You need huge amounts of equipment to do that.
Good point. Good point.
So I'd say if you're using an X sensor, just try and find another sensor that is at least twice, thrice, 4 times uh, better in terms of accuracy, uh, stability, because there are a lot of other things involved. Right? You cannot
Yes.
have just if you have a sensor that's accurate but not stable, it's pointless,
Hmm.
or the other way around. So there are a lot of parameters involved: tolerance, stability, drift. Uh, let's say a sensor that's accurate, but you have to keep setting zero every week. That
Hmm.
means it's drifting all the time, which again
Hmm.
is of not much of use.
Good point. Good
Uh,
point.
it's going to be quite a task hunting out uh, not just the sensors that we need, but also the sensors that we track as standards that are a level better than the ones that we need. We need to do both
Hmm.
of those. Uh, both of that work needs to be done. Finding
Hmm.
those kind of sensors.
So, to ask you a general question for other people who might be listening to the Hangout in the future, Anil, how would you recommend that citizen science groups like ours in their cities in India, how would they go about trying to find these reference sensors? So, in our case in Chennai, we are talking to a major university, a health university that might be providing us their lab equipment, which has reference sensors.
Okay.
Would you recommend getting in touch with the environmental health departments of universities in their cities, or talk to the meteorological department or the pollution control board? How would you recommend? What would the maybe 2 or 3 approaches to that be?
Yeah, one way would be to, I mean, these are the kind of agencies that have the resources to set this kind of setup, right? It's an expensive thing and
Hmm.
it costs a lot of money to keep it running. Uh, Buying is expensive, but then running it is also equally expensive. So it needs a lot of wherewithal to set up a laboratory with controlled conditions, with equipment, with manpower, and all of the other stuff required to run the show.
Hmm. So,
So as of now, one approach would be to involve the pollution control board, and the other is the central nodal authority that does everything that's related to laboratories in India. It's called the NAB, or the National Accreditation Board for Laboratories. Basically, it's the body that certifies the laboratories. So basically, a laboratory is useless if it isn't certified, right?
hmm, hmm.
If it isn't, you aren't sure about its standards and its performance. So the nodal body does that, and it assures you that if you do a calibration in Bangalore or if you do a calibration in Bombay, as long as the laboratories are certified, uh, you're good enough in terms of performance.
Understood. Understood.
Uh,
And also for a project like ours, which should be resourceful and independent, whilst the need for calibration labs and certified labs is obviously paramount in the future, would you
yeah.
recommend in the current term trying to come up with our own, hacking our own calibration chamber? Something simple that we could pick up in the literature, like, for example, a talcum powder idea.
Yeah, I
Um,
definitely thought of creating a little box, a black box or a suitcase kind of a thing, that can act as some kind of a secondary or a tertiary standard.
Okay.
Uh, Even if it is just a little bit better than the sensors that we are using, it's good enough.
Correct.
Uh,
Okay.
but we
So,
need to figure out how best to achieve that. It's not
hmm,
really an easy task, but
done.
something that needs to be done for sure.
Agni will put that down as a major activity then within our calibration
Yeah,
procedure.
yeah, yeah.
I'm sure,
Okay,
yeah, this
good.
has to be a separate parallel activity altogether to make sure that we
Done.
set up the calibration tool chain, as I would call it,
Good,
for
good
doing that.
advice. So we're planning to, we haven't fixed on this as yet, but as we were mentioning earlier, our intermediate reference sensor will probably be the Dylos, which is a laser, as opposed, and the our primary sensors will be air beams, which use LEDs.
Okay.
So because the Dylos use a laser, we're assuming that the accuracy of these sensors is higher, and other tests around the world have proved it out that the
Okay.
Dylos is actually quite accurate in indoor conditions,
Okay.
and can actually serve as the intermediate sensor we're talking.
Okay. Perfect.
So you would recommend basically primary sensor, intermediate sensor, and reference sensor obviously all being calibrated together, and calibration curves being created for all of them. How would you do that? Now that you have this intermediate sensor, how would you do that?
Yeah, you would have to do it all together simultaneously because uh, that's the only way to get the correct data. You cannot put, let's say, one sensor in a test unit, remove that and put another one and hope to get the same results.
Mm, mm,
So you would have to do relative calibration as against absolute. Absolute is when you can just test one sensor without any additional sensors being used for calibration.
right, right,
But
right.
we will have to do relative. That means at least two sensors or maybe three. Uh, the standard, the intermediate, and the tertiary all being put together at the same time, in the same conditions, at the same time, and measure data from all of them.
Understood. So just thinking aloud, basically you place the Dylos, you place the air beam and the reference sensor all together in the same PM chamber,
Let
develop
me
calibration curves.
Sorry,
Right.
let me interrupt you.
Go
Let
ahead,
me
please.
correct myself. I would rather not use the dialers all the time because it's my primary standard and it's been
Mm,
calibrated against an even better standard. So
mm,
I'd like to preserve it and make sure that it maintains its calibration for as long as possible because it's
mm.
again an expensive process. The thing itself costs a lot of money and then calibrating itself is again a lot of money. So the idea is to conserve your primary standard as long as you possibly can in terms
Mm.
because of economies. So usually your primary standard you try to conserve as much as you can and instead use your intermediate sensor and the unknown sensor and do those as often as you can and then compare the intermediate sensor with the primary one maybe once in a longer period of time.
I see, I see, I see. So understood. So there would be certainly periodicities between would be quite different.
Yeah, just to give you an example,
Understood.
for example, when you take calibration of light, you would have a primary standard lamp that you calibrated at, let's say, a central laboratory. And when you bring it back to your laboratory, using that particular lamp, you in turn calibrate your own set of secondary standards.
Hmm.
And then you use those secondary standards all the time, whereas the primary is kept aside and not used quite often because you want to conserve its calibration.
Understood. By conserve its calibration, you mean basically protect the equipment.
Protect it from because okay, let's say like I said again going back to example of the light bulb. Every time you switch it on and switch it off, it's undergoing stress.
True.
Uh, its light output levels are going down, and so on. If it's not done in proper controlled conditions, temperature, humidity, electrical voltage, the current going through it, and so on, it would damage its filament, for example. You don't want this happening too often. Every time you switch it on, it's likely to get a little further damage to the filament. So you don't want your primary standard to be operated uh, continuously or too often.
Understood.
You would only use it for a few times when you want to calibrate your intermediate standards.
Understood. Understood. Thank you for that, Arnold. Agni, any ideas on that idea? Because it's going to be a very, very important part to our calibration procedure,
So,
I would expect.
and to go further on that, for example, let's say when the whole network is set up, you could have a set of, let's say, 10 dyno sensors, which are in turn used to calibrate 100 intermediate sensors. And those 100 are in turn used to calibrate 1000 air quality monitors.
Mm.
So you would set up a chain of that kind of thing. And then the 10 dynos units that you have, you intercompare with each other to make sure that they are staying within range. And
Yes.
then a few of them, you get them calibrated at the central laboratory. So you don't have to
Okay.
calibrate all 10 of those dynos units. So that's going to be extremely expensive.
Excellent point.
Um, Anul,
Yeah.
what we were doing is like we thought of a method that basically we found out that different combustibles like let's say agarbattis, dhoop, and your smoke coils, mortine specifically,
Yeah.
we found ppm data for all of these. So we were thinking of creating a chamber which and possibly use these as calibration standards. Is it a good idea?
I wouldn't say so, not at all, because the variances between those products will be extremely high. You just cannot be sure that one coil against the other coil is going to give consistent results. If the
True.
variation is larger than the sensor that you're trying to calibrate, it's really going.
Definitely.
Yeah.
Although what you can do is use it as a source of the uh, particulate matter or smoke, and
Hmm.
have an intermediate sensor and an unknown sensor, measure that value, and you find the difference. So your standard is still your intermediate sensor, not the smoke coil or whatever else you're using. Just a
We yeah.
generating device.
Mm.
So we were thinking pretty much on the same lines then. So what we thought of was to have what we were doing is somebody in our space came up with something like a vortex generator for aeration.
Okay.
So we were thinking of using the same thing to bring in smoke and mix smoke with air in a environment which does not have smoke at all, which would be a box ideally. Or I'm not really sure about the shape right now. So
Remember, when you're generating anything, you need feedback as well, right?
yes, yes, yes. So
So
the housing itself was
if you
pretty
have an
good.
engine that's running, you need to measure its speed to know how fast it is going. So you need a sensor.
Yeah,
Same thing with your idea. If you're generating smoke, you still need a sensor to find out how much smoke
yes.
you're generating.
Yeah.
So
Very
it all
true.
boils down to having an intermediate sensor. Eventually, it's a sensor that is
Yeah.
more important, not the method how you generate the smoke. That
Yeah.
part is that is trivial. You can generate it in 100 different ways.
No, the point what I was coming to was the fact that we came up with this idea of putting two sensors, an intermediary and the thing that we're measuring,
Yeah.
together in that chamber. But the issue is, with respect to airflow, there's this minor problem that I cannot have the concentration increasing by itself. What I mean by that is that if you're pumping in air, or basically adding a PM concentration to air, you're fundamentally adding air to the existing amount already,
Okay.
right? So you have to have an exhaust vent, like a
Okay.
flow, like something to allow air to flow outside.
Yeah.
Now the thing is, I'm continuously losing pollutant levels there also. So what do I do about it?
Uh, Add more sensors, one at the inlet, one at the outlet, and monitor those to give
Ah,
you
definitely,
more feedback.
definitely.
So
Thank you.
basically, you form a feedback loop, and it's like PID if you're doing electronics. You
Yeah.
tune your airflow by measuring the inlet and outlet. And so.
Definitely. Wonderful. Thank you.
But because more complex, right, and expensive.
Yeah.
But the good thing is, once we do that initial characterization, that becomes the major headache. Well, I'm not going to call it a headache, but a major point of proving or validating our data. And then once that's done, like Anul was saying, we use the intermediate sensors for the recalibration.
That's right.
Yes.
So you're right, Agni. We do need to understand what the challenge concentrations are entering the gas chamber, because that will determine. Obviously, the reference sensor gives us a value. We still need to know what it's calibrating for. Is it at 300 ppm or 250 ppm? Isn't that right, Anil? Your suggestion is we don't need to worry about the challenge concentrations, or do we need to worry about the challenge concentrations?
We need to worry insofar as we don't exceed saturation levels.
Okay.
That's about.
But shouldn't we know that, say, a certain PM value is entering the chamber? Because sure, the reference can give us a reading, but unless we then, when we take it to field, unless we know what, since we're trying to measure different concentrations, how do we recalibrate? How do we calibrate using the calibration curve unless we know approximately what the challenge concentration is?
That's a difficult task. Maybe what could be done is set up independent chambers where we have known concentration. So we don't try and do 10%, 20%, 30% in one chamber. We have three different chambers, 10, 20, and 30%, and we calibrate three times. It's just an idea I had now. That's one way of doing. So you're only worried about maintaining one particular concentration in each chamber and putting in sensors and checking if it falls within the required limits or not.
Absolutely. Agni, I know that David Holschuss, who did his PhD in commodity sensors, in his paper he describes a chamber, a low-cost chamber that he came up with, where he was able to place multiple sensors in at the same time and do some calibration work. We'll follow up with, we'll send that to Anil as well, and we can review that to see if his idea matches up with what David did, and see where we can go to from there.
That sounds promising.
Absolutely. He came up with a really smart way of doing it, as you were suggesting.
So just so I recap myself, the things that we're trying to measure is temperature, humidity, particulate matter, and gases, right? Pollutants.
Yeah, NO2, CO2, and am I missing something?
Well, at this point in time, those are the pollutants we're measuring: NO2, CO2, and particulate matter, 2.5 and PM10.
For PM10 also?
PM10 is still an important pollutant for India. Agni. It is still an important pollutant. In a lot of other developed countries, because of diesel, the lack of diesel is often a major contributor to PM10. And they don't really use it in developed countries, so it's not really that much of a problem. But India, as you know, diesel, that's in fact one of the major contributors of PM10.
So these numbers refer to the size of the particles in microns. So PM10 is the 10 micron.
Correct. Anything 10 microns and less is PM10, 2.5 microns and less is PM2.5.
No. It's PM 2.5 is 2.5 to 10 microns, and PM10 is 10 above.
Okay.
As far as what I understand, let me just check. I'm not sure.
We can look at that separately. Absolutely. So, Anu, now how would you? Yes.
The other thought, just while you were talking, the other thought I had is the one industry that does a lot of controlled environment is semiconductor manufacturing. These plants require very specific levels of ppm concentrations in terms of matter and so on. So they have obviously developed all the processes, sensors, and calibration techniques needed to keep it running continuously and in large scale. There are tons and tons of fabrication labs everywhere. I'm sure they have hundreds, thousands of sensors. So we should probably try and look at that kind of sources and see if we can dig up some information about how it is managed in those kind of situations and see if that helps us.
Excellent point. So we can develop our calibration sensors using those. Obviously, these guys have resources that they can throw at it, but we can certainly learn how they do it and certainly
Exactly.
glean
Yeah.
something useful.
It's a different situation, but it can help us in some way.
You bring up an interesting point, Anil. A lot of our sensors don't do very well at very low concentrations and very high concentrations. Since we are more about screening and assessing, we're not as worried about low concentrations as high concentrations.
Okay.
So, in fact, I think we were discussing this with Workbench the other day. Should we look at trying to adapt our sensors for the application you were mentioning earlier, which is, for example, testing the purity of air in semiconductor labs? And because our sensors can't perform very well at extremely low concentrations, unfortunately, that's not an application.
Right.
But nonetheless, at high concentrations and medium high concentrations, it does quite well. Very high concentrations, as you were saying again, it saturates. So very high and very low concentrations, unfortunately, I don't know how much accuracy we can achieve, but we can certainly characterize it for a very large dynamic range, though, nonetheless.
And quite often, what's usually done is when you have a sensor with a limited range and you need to measure beyond, it becomes obvious that you need another sensor that can operate in the next higher range. If you want to really cover the high concentration. So maybe we need to look at a sensor that can measure higher. If our existing sensor is getting saturated at certain levels, then we need another sensor that works in that particular range to be able to get any meaningful data results.
Right, right.
So I'm not sure if the sensors are available in various ranges or bands, but if they are, then that's what we probably need.
Good idea. So we, rather than trying to do a 100-point calibration curve, we should do it in bands.
Yeah, we
So-
can't have a one thing fit all scenario in this. We need to have maybe multiple sensors to cover the whole range. Most likely.
Good point. So to clarify, just PM2.5 and PM10, Agni, thank you for bringing it up. Basically, PM10 are 2.5 to 10 micrometers in diameter,
Okay.
and PM2.5 are 2.5 micrometers in diameter or smaller.
Smaller. That's what I would have imagined.
Yeah.
Correct. Thank you for clarifying that, Agni. Agni, do you have any further questions whilst we have Anul here? Because I'd like to think about the next steps of how we can proceed from here.
Yeah, Anul, before we can proceed, I would want to know, like, what exactly we came up with machine learning to be used for calibration. Now, is it for anything other than using regression curves? Regression fits, yeah.
I would know. I'm not really a math guy on this, so probably the wrong question for me. I don't think I can add much insight to that question.
I think we can involve David Holschius again in this, Agni. I'll try and bring him to a hangout with all of us.
Okay.
Definitely.
And he can shed light on these issues of the gas chamber, the chamber, and regarding the regression curves.
Definitely.
Unfortunately, well, not unfortunately, but I think the regression curves are the simplest and the best understood method for doing this. When you're looking at
my question
nonlinear
was-
values, yeah.
So what I was asking was if there's something else that machine learning does. I understand that regression curves are important,
Yeah,
but
yeah.
I was wondering if there's something other than that they're using, like not the part of fitting the curve to the data, but if machine learning does something completely different other than that too.
What could it do besides that, do you think? I mean, in what other areas could machine learning be? Something to think about. See, the thing is, right now we're working with passive sensors.
Yeah.
There could be a day when we have active sensors and then data sent back from the cloud to the sensor can actually do something locally. Anul, any thoughts on that? How do you see that going?
It's difficult to say. It's cutting edge.
that is a whole different ballgame. Very true.
Yeah, it depends on how the sensor manufacturers think about new ideas of measurement. But yeah, you could never say. We probably could have some breakthrough. We got to work with what we have right now, which isn't.
Absolutely. And first step is obviously understanding our issue first before we can proceed. I have a couple of follow-up questions, Anil. Now, this idea of network calibration and blind calibration. So these guys basically, as we were talking about earlier, they use the readings from primary sense, that is primary sensing devices in the network,
Okay.
to somehow flood the network with a recalibration
Baseline.
factor.
That's a baseline
Which,
values.
right. Do you know how that works? How does network calibration, on the fly
As well
calibration
as
work?
what I told you earlier, that we have a couple of reference units that are always in controlled conditions, and you take that data and compare it with the others. So it's not really exactly the same thing, right? You have sensor data
Right.
coming in from a standard controlled environmental monitoring unit, which you know is maintained at a fixed concentration level, fixed humidity, fixed temperature.
Mm.
Uh, so that sets the baseline for all the rest of your units,
Good point. Good point. So that becomes the recalibration constant.
more or less.
Recalibration factor. It's not a constant, it's a recalibration factor
Yeah.
that is derived from our reference sensors that have been
Yeah.
continuing alongside our field sensors.
Yes.
Okay.
Is this
So the
recalibration
way
factor a dynamic value?
for example, the way it works is, let's say you have a standard running continuously at 25 degrees Celsius, and you have an unknown unit which was calibrated at that same 25 degrees Celsius in the lab and then sent out to the field.
Mm.
Once it goes into the field, that base value of 25, which it was originally calibrated at, could drift either way depending on the huge number of circumstances. So if it is able to receive once again the data for that 25 degrees Celsius value from a reference which is being maintained at that particular value standard, then it knows how much to shift the curve uh, up or down to compensate for that variation due to change in location and position.
Good point. Good point. But unfortunately, drift is random, right? It can be both positive and negative, can't it?
It could be both ways, which is why, since your reference is always at a fixed value, you know
Yes.
which way the one in the field is drifting. Because it has the field values already stored in from an earlier calibration, let's say a month ago, and then you measure it, comparing it, let's say every day or every week, and seeing whether it's whether the reading of 25 degrees from a week ago and now is it increasing or decreasing.
Good point. Right. Agni, does that make sense to you?
Yes. Yes.
I need to run through it in my own head because this is
Yeah.
quite new to me in the sense of how to do that. Once we have the flow chart of what's going to be doing which, I think then it's just a matter, like you say, of machine learning and programming it in. And luckily, our sensors are open source, so we can actually change all those things, right?
So maybe I can try and put this to a different perspective. Uh, Practically all of measuring instruments nowadays store calibration constants within their software. Right? So no matter what the value it is measuring, as long as it knows what it's supposed to show for a particular input, it just stores a certain factor within the software which it applies for all subsequent measurements. And that factor might change as time goes by because of the influence of temperature and pressure and humidity and so on.
Right.
And that's exactly why you need to recalibrate it every year, every whatever duration you feel like. And then that's when you reset that internal number to a new number, which once again matches your desired tolerance. So,
Point taken.
so once you have the calibration constants in software, then it becomes very easy to network all of your instruments, compare them, and change values dynamically as long as you have standards maintained at a fixed reference at one location.
Yeah. Good point. Good point. We can study that further also.
It's
I
a
think
bit
this is something
convoluted, yeah. Maybe it's difficult to kind of distill it in a few sentences.
Sure. I think you've given us the kernel of how it needs to be done. If we could put together a flowchart, a process flowchart, I think we'll have a better idea.
Yeah, that'll be much better.
And as next step, I'll involve David Holschuss as well and figure out when we can chat with him and understand how calibration works from this perspective.
Right.
I should mention to you, he did something interesting. So generally with these sensor systems, we have only one sensor in each sensor package. What he's done is he's looked at multiple sensors within a sensor package.
Okay.
That way you can do an averaging, a local averaging as well across, say, 2 or 3 sensors within each package. The idea being that if there's also a smart thing, because if sensors fail on the field, then you can just reroute
Swap
to a
them.
different sensor. Exactly.
Yeah.
So maintenance becomes easier. The cost of these sensors is quite low, so that way you can throw more sensors into a package and not have the BOM go up too much.
Exactly.
So it's like a hyper-local calibration, hyper-local averaging, and then obviously it flows down the network in terms of the calibration factor.
Yeah.
Agni, does that? What do you think of that idea?
That would be a smart thing to do, and I was going to
Right.
suggest it a while ago, is to have multiple sensors within your unit, one exposed to the phenomena you're trying to measure, and one not exposed to the same phenomena. And by comparing the values of both of these sensors, you can know easily what's going on. Much better, much better than if you're just one sensor which you are looking at.
Interesting
So
idea.
it's
That
like
way,
having a reference all the time within your device. It may not be as accurate, but it gives you a much better control over measurement.
Interesting idea. Okay, so you basically innovated on his idea. So you use, rather than actively exposing all sensors within a package, you use one as a dummy. Well, obviously not as a dummy, but as your local
passive sensor. Yeah.
What do you think of that, Agni?
It's pretty interesting. I would want to see if how this works. I have not really tested it to begin with.
That's a great idea. That's a great idea.
This comes from, let's say, electrical calibration. For example, if you're trying to measure frequency, one way of doing it is to have a very precise frequency inside of your instrument and compare your external one with it to know the difference. So it's very easy to measure. The same way you do it with the physical phenomena of measuring particulate matter. Have a reference sensor inside your equipment and one that is exposed to your environment.
Good point. Good point. But in our case, the reference sensor will be the primary sensor, the same kind of sensor, except it won't go through the same exposure processes as the active sensor. So you basically have an active sensor, active primary, and a passive primary.
That's right.
Interesting idea. Agni, it's almost been an hour. Would you like to wrap up? Any further questions? What would you see as the next steps?
I would rather let's start with making the calibration chamber first now. Because we either ways need one, and even testing it in random environments will do us no good right now. I guess we should first build the chamber.
Anil, would you recommend obviously chamber, but also trying to figure out what our overall process is first?
That was the first thought that crossed my mind, because easy saying build a chamber, but the other thing what you need is a chamber that has fixed or controllable temperature, humidity, and pressure. You need a means of introducing your pollutant inside the chamber at a known rate or value, and exhausting the whole thing. Exhausting in terms of removing it out. Again, it probably had a control to it.
How do you suggest we do it?
Yeah. For all of these, you're going to need sensors. Temperature is going to need temp sensor. By temperature, I mean maintaining or measuring the temperature of the chamber would need its own temperature sensor. Also its own humidity sensor, and possibly PM and other sensors at the inlet and outlet to figure out how much you're introducing in and how much you're exhausting out. Then you're going to need your reference standard sensors, which will be the calibrated ones that you will use to check the unknown ones against.
Right.
Those sensors, your first worry would be, how are you going to get them calibrated? Is there someone who can do it for you? Ram, you mentioned someone in the university in Chennai. So if they can do it, awesome. That would be a good starting point.
Would you
Uh,
repeat that, Anu? I didn't catch the name of the organization.
the university in Chennai that you said
Yes,
would
yes, yes, of
help.
course.
Yeah.
Yes, indeed.
So maybe
Yes, I would.
a good start would be to actually visit them and see what facility they have,
Absolutely,
what equipment
absolutely.
they have got, and how they are running that show. That gives
Good
us an
idea.
idea of what we need to do has a level of accuracy below what they are doing.
Good idea. Good idea. So if we go there with a little bit of data, I mean not data, but at least a process of our own, we
Yes.
can we can because ultimately, Agni, they're going to be our partners in calibration. So
Yes.
Yes.
we'll need to explain to them what our own setup is and how we can use their setup and our setup in a rational fashion.
Yes.
Because ultimately we can't go back to them too often. So they're doing us a favor, and we need to figure out
Yeah.
if we can approximate their chamber with our chamber as well.
Sriram, what
Yes,
I can temporarily do is, as long as I'm in Manipal, I'll use our own emission testing lab for that. So I believe they have NO2, CO, and CO2. I'm not sure, but I think they have.
that's great. That'd be very useful. That'd be very
Yeah, yeah.
useful.
And since I can walk in any time, it won't be an issue to calibrate. They'll lend us the sensors.
Correct. But as a measure of
Okay.
sustainability and to keep costs down, we have to come up with our own chamber
Yes.
ultimately. Anu, would you say that's fair?
Yes. Also, at the same time, it would be nice not to reinvent the wheel. So it's better to check out and see what the
Exactly.
laboratories have and see
Yes.
if we can either replicate that or make our own. Oh wow, I'm seeing a drone on television. Sorry, got distracted for a while. There's a
and to
drone
do a
and stuff.
literature and to do a literature review and figure out what makeshift chambers we can build as well on our own.
Yeah. And again, I hope someone's taking notes because there are few points that I'm remembering as I talk, and hope someone's
Absolutely.
writing down. Is we have quite a fair number of automobile test laboratories within India. Uh, these are extremely well equipped to handle all kinds of tests, including emissions and so on. The primary one in India is called DRA, the Automotive Research Association of India, located in Pune. So maybe a visit to them might prove useful sometime in the future to understand how they measure emission and so on.
Absolutely.
There are a couple of
Absolutely.
other similar labs. There's a defense lab for vehicle research development establishment in Aurangabad. Uh, they could be useful as well. So there are a few of these uh, uh, government run labs which can really help us a lot in calibration aspect. And sometimes
Absolutely.
even just visiting them and talking to them to tell us a lot about the kind of equipment we're using and process we're using and so on.
That's a
So
great
that's
idea. We'll
useful information.
certainly kick all that stone and pursue that.
Yeah.
Um, that sounds good. Agni, as a first step, perhaps you and I should chat offline about in terms of the calibration procedure that we've come up with,
Definitely.
and use that as a document to try and interest other people like the University in Chennai, the Pollution Control Board.
Yeah.
And in the meantime, we look at what's out there in the literature about makeshift chambers that might already be available.
Yes. Anul, there's one more thing that I'm quite worried about is that we had some people helping us with CFD.
Okay.
So what these guys were saying is that altitude is also an important factor in with respect to sensor placement. Uh, do you think so? Because ideally, if you're at sea level, you'll have a different sort of an air pressure, hence a different air distribution. So your microenvironment might be more compact or larger. I don't really understand like how, but
Okay.
yeah,
Relative pressure, or let's say height above mean sea level.
yeah,
Yeah, it could affect at least those sensors that interact with air. So that includes that excludes temperature and possibly humidity as well. But it does impact your
main
NO
sensors.
and carbon monoxide and particulate sensors. I'd say that's another graph or curve that the manufacturer needs to let us know is how linear the sensor is over pressure.
It's
So if
not
you
an
know the
easy.
linearity, again,
Yeah.
if it's a complex curve, then again we need to add some more maths to the equation.
This is not
That
an
would be
easy thing to
unfortunate.
do, right, Anil?
Yeah,
Because we
not
taking
at all.
reference sensors at different heights. These are very heavy
Yeah,
objects.
not at
It's
all.
going to be very difficult to calibrate for
So
a primary reference.
the way the labs do it is, of course, to put them in chambers where you can also adjust the pressure, and hence that
Good idea, of
that
course.
relates to the, the height of the
Good
wings.
point. Good point. Good point. Negative
So
pressure,
even
positive. Yeah,
the
that's yeah.
so even a chamber that if we decide to make one, we have to have a means of pressurizing or depressurizing it. That relates to altitude.
Um, that's an important thing to do, Agni. You brought up an important point about the fact that most of these projects are human exposure. So
Yeah.
they look at 5 feet. I think 4 to 5 feet is what they try and do it at. But if we are going to be looking at characterizing air quality on a broader level, then we will have to do height variation as well. You're right about that.
Yeah,
But that
because
is an advanced.
Mumbai is, let's say, mean sea level, but a town like Ooty would be several thousand feet in the air. So it's quite a difference.
Absolutely. In fact, a very interesting project would be to look at how exposures change with apartment buildings, within apartment buildings.
Yeah, that could be.
And that could be something we could quite try it out as well, where we have makers, who live in apartment buildings at different heights.
Yeah.
That could be something we could look at. But that would be an advanced step, Agni, because our chamber would have to be pressurized, like Anil was saying,
Yes.
and
Yes.
that's not going to be that's non-trivial, right? Anil, how would you pressurize a chamber? Very basic question.
Need a compressor and then some more sensors to control
Essentially,
that pressure.
and
So
then a
it's adding
vacuum.
more sensors. Yeah, I mean the compressor works both ways. Either pushes
True,
air in or sucks it out.
true, 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 true. A pump. Yeah, good point. Agni, over to you. I have several more questions for Anil. I'd love to keep talking. However, I realize it's quite late for you guys.
I'm cool.
Anil,
I'm fine.
great, great. In that case, I think the next immediate steps is let me see if I can set up a chat with David and our colleague in the college in Madras. Even if she can't be on this, if she can nominate someone who runs their calibration labs to be a part of our conversation, I think that would be very useful.
Okay.
Because ultimately we have to work with local calibration partners. So I think bringing them into the conversation now would be a good idea. So Agni, you and I probably from this chat, post chat, we'll put down a minutes and figure out
Sure.
what the next steps are going to be.
Definitely.
Anil, any parting thoughts?
No, just one. If you're trying to locate labs that can do this kind of work, there is a resource available that you have to find them. That's the NABL, the National Accreditation Board for Testing in Can Laboratory. It's NABL-India.org.
Any national? Could you repeat the?
Accreditation. Yeah, November Alpha Bravo Lima
Yeah. Okay.
dash
Okay.
India.org. So they have a list of laboratories that are accredited under various parameters: physical, mechanical,
Excellent.
environmental, chemical, and so on. So
Excellent. Excellent.
the
That's very
starting point
useful.
would be to see if there are any laboratories already accredited. If there aren't, then we are in bigger trouble than we thought we would be.
Absolutely. It would also be useful, I mean, just to get an understanding of the costs involved with
Yes.
calibration.
Exactly.
Do they do it on a sensor basis? Is it based on time,
Yeah.
throughput? It would be interesting to figure those things out as well, I think.
Yeah, Anul, how do you generally heat a chamber? What do you use exactly?
Actually, electrically is the easiest because you can really control it very accurately. So use heating element and a PID control loop to and again a sensor to measure temperature.
Okay.
That's how.
We get thermal controllers. Should I get one of them or something?
Uh, Not right away unless you have a design ready, because you need to decide what kind of controller
Yeah.
will be useful.
Oh, okay.
Agni,
Because
let's work out our calibration procedure. At least get a draft going.
yeah,
Yeah.
And once we understand the components, the system, and then the components, we can figure out how to fit in these
yeah,
different components
and
as well.
the bill of materials will come later. Exactly what we
Exactly.
need.
Exactly.
Still
Exactly.
need to work out the broader specifics first.
The detail. So this has been a great high-level chat, Anil. Thank you very much. I certainly feel a lot more confident about taking this on.
Pleasure.
And Agni, you and I will take things offline, and obviously Venkat has been a part of this conversation as well. Venkat, how are you? Venkat.
I
He's
think.
probably muted.
Yes, I'm there. I'm
Oh,
there,
good.
but
Hey, Venkat. Do
the
you
thing
want to
is,
add your own thoughts? Yeah.
yeah, I was there in the whole conversation, but the thing is, the voice was breaking, as I told you previously. But Anu, hey
Yeah,
Anu,
yeah. Hi,
yeah,
Venkat.
how do you do? It's
All
been
right.
long
Hi.
since we met.
It's been nice
Yeah,
talking to you all of you guys.
yes, I was
Absolutely,
able to.
absolutely.
Yeah, regarding whatever we have discussed, it's a whole new level that what we were thinking right now, like
Okay.
using extra sensor for the same device and all.
Uh,
Yeah, we could go on those things and build up a whole different calibration thing.
yeah, I mean it's not easy. Calibration is some parameters are very easy, whereas others are really very tricky.
I'm extremely sorry,
Absolutely.
guys. I'm able to listen to half of the things right now.
Right.
Sorry.
Right,
For
right.
example, if you consider human
Internet
senses,
problem.
the calibration of audio or the ear-related function is pretty much well defined. Sight, light is a little bit better. Uh, Nose or smells. It's, I don't think you've ever heard of calibration mechanisms for smell. It's extremely difficult.
Interesting, very interesting.
Same,
Okay.
same with taste. Taste is even worse. You can just categorize as hot or cold or sour. Or, you can't give a number specific to the sense of the term. So certain parameters are extremely difficult. You can easily measure pressure, for example. You can easily measure velocity or acceleration. But things like what we are trying to do, particulate matter or concentration of gases, not that uh, easy. Temperature,
Not easy.
pressure, humidity is not really a big problem. Those are extremely easy to calibrate
And those will be
and
your
measure.
three major factors. The others, Anil, that are X factors right now, we're still debating as to the influence they'll have on values is ambient light and wind flow.
Mm-hmm. Ambient light
Those
wouldn't affect any of these sensors you're using, right? Unless you have
um,
any data otherwise.
Luckily, the baffles that they use to absorb light, ambient light, and to prevent ingress of ambient light are quite good. But a lot of these say in outdoor conditions where you have light pollution, basically it's light pollution, then it does skew the readings.
For
Um,
which particular
for
sensor?
the dialos, so all of these sensors, if you place them in ambient light, we haven't tested it out. They generally say you don't. Ambient light is definitely a factor in these in providing accurate readings.
I guess so,
And
because eventually, the diverse example, laser is essentially a source of light, and the
correct,
sensor coupled to it is measuring light, so it would affect for the
definitely,
diagonals. But the ones
definitely.
that work uh, on the LEDs would probably also be equally effective. Yes, okay.
Correct.
Yeah,
Oh, yes. The reference sensors won't obviously be affected by ambient light. It's not going to
right.
be a factor. But unfortunately, our primary sensors are going to be affected by ambient
They will
light.
be. Yes.
So, because a lot of applications that involve placing these devices outside in semi-outdoor conditions,
Right.
even though they're supposed to be only for indoor conditions, our applications will require us to look at adapting these devices for semi-outdoor conditions.
Right.
in which case ambient light will become a factor, not so much for the gas sensors, but for the particle matter sensors.
And wind flow will definitely be a big major factor for sure.
Yes. We've done some quick testing, and unfortunately, I mean, by quick testing, I mean literally my blowing in the exhaust inlet valves. That's a highly accurate calibration that we'll be doing. But so far it seems like wind flow doesn't affect it. However, I'm looking at, we're obviously talking about strong gusts of wind. But that would be an interesting thing to look at as well, I think. We'll have to figure that out, because they basically have small fans that are sucking air in,
Okay.
and also exhausting the air. So we need to figure out how that plays a part in all of this. One idea we had was to look at pressure between the inlet and outlet valves, and if we can come up with a mechanism by which we equalize the pressure of the inlet and outlet valves. If we can do that, that means that the airflow is steady.
Yeah.
That's an idea we have. We'll pursue that separately.
There's quite a different ways of measuring airflow. The easiest nowadays is what's known as the hot wire anemometer. Essentially, you take a little piece of wire and heat it at an extremely controlled current so that the temperature is extremely fixed. And then see how much it changes as airflow flows over it. That gives you a very precise measure of airflow. So most modern airflow measurements are done using this hot wire measurement. It's essentially a bridge. So you have three elements that are fixed, and the fourth one is variable. That tells you exactly how the so that's easier to measure than pressure, because pressure is the response time of the pressure sensors is not as fast as those for temperature sensors. That's another thing to consider for every sensor that you use, is how quickly does it respond to changes in.
Good point. Because that's part of our profiling of the sensors as well, that we're looking at will be rise times. And remember, we're talking about that initially, Agni, rise times and settling times and those factors. We'll take that into account. Anil, I think we should wrap up. I don't want to take any more of your time and Agni's and Venkat's. It's late. Indeed. It's been great though. We've learned a lot, and we'll take up a work plan separately, and we'll get back to you on that.
Yeah, no pleasure. We can have these meetings at regular intervals as work progresses.
Absolutely. Perhaps every week, every 2 weeks. Agni we'll discuss that offline, and depending on Anil's schedule, we'll work that in.
Sure.
Sounds good. Thank you all. Agni, if you can just send us a link to the video, that'd be great afterwards. Thank you, Anil.
Definitely.
Pleasure.
Okay, Venkat. Agni, pleasure. Thank you again. Bye. Good night to you.
Thank you. Good night.